Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my distinct pleasure to introduce Dieter Fox from UW, which is just across the lake from here. And Dieter has been working on robotics and also estimation problems involving data from sensors on either on robots or instruments in the environment. And what he's going to talk about is some recent work he has been doing in collaboration with actually quite a large number of people there, and very interesting work about recognizing human and other activities using data from sensors, instrumented or wearable sensors. So with that, Dieter.
Great. Thanks a lot for having me over, and thanks a lot for coming to the talk. It's great to be back. It's actually the first time I'm talking here as a non-robotics person, so we won't see any robots today. But as you might see, many of the techniques we are applying actually very similar to the techniques we are doing with robots. So in a sense, whether you want to localize a robot in an environment is similar to figuring out what a person is doing right now. Okay, so in a sense you get a stream of sensor data and you try to interpret that with some probabilistic techniques. So first I'd like to acknowledge some collaborators with several faculty at UW, Jeff Bilms, Henry Counts, and Gaetano Borriello. These are all the grad students who worked on that, and I highlight Lin Liao because more than the first half of the talk is based virtually only on his work. So everything that has to do with extracting information from GPS is stuff that he has done. Then we have a pretty strong collaboration with Intel Research Seattle. Some people there, especially also Tanzim Chowdhury, Dirk Hanel, Anthony Lamarca, Matai Philippos. And funding is coming, DARPA, NSF, also MSR, and some recent funding from Toyota. And hopefully we can start some more collaboration here, also based on the work that's going on. So as a context, so we started the Assisted Cognition project about 5 years ago with Henry Kautz. And the idea was to help people with cognitive disabilities during their everyday life. So imagine now that we have more and more sensors that we can, for example, have people carrying sensors or sensors that we can put in the environment, that now maybe you are able to help people, for example, with Alzheimer's disease. So for instance, what happens a lot to these people, they might, if they are outdoors, they might just get lost. Okay, so you might want to have a system that can detect when they get lost and get them back on track, so to show them how to get back home. Or also during everyday activities, they might just forget what should be the next step they should perform in a multi-step task. And the idea is that now if you have a system that can keep track of what the person is doing, then that system might actually be able to suggest the next step and prompt them on what they should be doing. Another very important application is actually long-term healthcare monitoring. It turns out that it's an extremely important problem to track the activities elderly people are performing every day over long periods of time. So, and this set of activities is called activities of daily living, such as going to the bathroom, cooking, brushing your teeth, taking medications and these things. And you can imagine if your environment would be able to track those activities over months, and this solidly based on sensor data, then you could maybe early on detect when a person, for example, significantly deviates from those patterns of the recent past, and then you could maybe intervene early on rather than waiting until a real crisis comes up. Okay, so this is most of the motivation behind that. Later on I'll show you also some work in the context of some military applications. Why do I worry about locations? One thing is, of course, because that's what I did for my PhD thesis on robots. I guess that is also related to that. But on the other hand, it's very obvious that if you know where a person is, that clearly helps you in figuring out what the person is doing, and that gives you valuable context information. So for example, if you pick up a toothpaste, if you do that at home versus you do that maybe in a supermarket, it's a very different purpose. Okay, so it gives you valuable context information for what people are doing, where they are going. Also very much related to what Microsoft's working on, location-based services, MedPoint-related services. And we also work with Tanzim Chowdhury especially on an NSF study where we collect data from an incoming class of graduate students, 25 grad students, they carry a sensor system for 1 week every month for the duration of 1 year. And the idea is that from the sensor data we would like to infer kind of the structure of the social network and how social networks evolve over time. Another aspect of that is if you know where the people are in the building, how they move through a building, you can also hopefully better understand how people use indoor spaces. Where do they meet? What is the correlation between the closeness of their rooms versus whether they collaborate and things like that. So this is very much for other applications of this research we're doing here.
You can touch upon the privacy part.
Oh, yes, we can discuss that. Do you want to do that now, or maybe better to the end? It's coming, and we had many discussions in the faculty on that. Because, for example, the students, they also record audio, and then even though the students sign an agreement, then suddenly when the student talks to, for example, a faculty, then suddenly they record that conversation. So clearly we are not allowed to store raw audio. We are only allowed to store features extracted from the audio that let us detect that a conversation is going on, but not what people talk about. Okay, very important. But then on the other hand, you could say, well, but then suddenly, if you get this location data, then you can estimate which student spends how much time in which faculty's office. Might not want to, no, sounds funny, but it's actually very interesting and serious implications, right, that we have to think about. And we also talked to the Attorney General's office to find out whether we are really in the range of legality and whether everything is okay, and he agreed that it's very much okay, but many of those issues you'll only figure out once they go to court, right, because there are no precedences right now. Just they have to catch up with all these new capabilities these sensors provide to us. Let me just give you an outline. You see there are quite some topics in here, so I'll just give kind of high-level ideas of most of the aspects. I just don't have time to go into the technical details, but we can clearly discuss these after the talk or during lunch or maybe later in other meetings. So first I'll talk about estimating transportation routines of a person based on traces of GPS data. So a person is carrying a GPS sensor, and we want to estimate when the person is getting on the bus and things like that. Then how you can use those traces also to learn something about the significant places of a person, like distinguishing between home and work in different locations. Then I'll briefly get into how you can kind of expand this type of area, the research, also into indoor environments where we use Wi-Fi 802.11 signal strength for localization, indoor and also outdoors. Then I'll talk about some more recent work using the multi-sensor board that was developed with Gaetano Borriello at Intel Research Seattle, and Gaetano is coming in June, so I guess you'll hear much more about that when he comes. But I'll show you some of the inference we're doing right now, and then time permitting also how we can use RFID tag to track activities of daily living of people. So the task of transportation routines is you have a stream of GPS data. So a person is carrying a GPS sensor around, let's say, for a week or a month, and we would like to extract from that data what are the typical goals of that person and on which routes does that person go there. So we want to then also be able to, on the fly, predict where the person is going to, which of those goals we've already seen. So in a sense we want to infer the location, but also mode of transportation, like walking, being on the car and bus, and then where the person will go. And later on I'll give you an example for how you can use that to detect when the person is taking actually a wrong route. And the information we're using is just, you can download that from the web. So we have a street map, which is kind of a graph structure representing the streets. We assume right now that the person is only moving along the edges of that graph. So in a sense, if there's a huge parking lot, then in a sense our system would guide the person around the parking lot because it might not be part of the graph. But I'll show you some examples of how we can handle that with other representations. Some very useful information is, of course, if you want to estimate whether the person is moving on the bus versus car, it's very useful to know where the bus stops are. And we can also get that from the web. GPS tracking, even though everybody, I guess with car navigation, everybody tells you it's a soft problem, it's trivial, but if you have a GPS that a person is carrying around, it turns out it's really bad, I guess, because people, they are much more often under trees, they go very close to buildings, right, and then you have this multipath propagation or blockage of satellite reception. So the GPS data you get when a person is carrying that around or sitting in the bus, for example, is actually pretty noisy. It's not as easy as people might think.
Question, do you find the newer chip generations?
The Surf 3?
Surf 3?
Yeah, sure.
Yeah.
we're using those, even with those.
So you're still finding a lot of that? I'm interested to get metrics from you about how bad it is later on.
I might, I don't have I think, but I might later show you some. Yeah, we just went last week to a DARPA evaluation. It's pretty bad.
Okay, great.
It depends even on whether there's sunshine or clouds and time of day. It's even with the new generation. There are always some people who tell you that with the new generation it even works indoors. It sometimes works indoors, right? But it's not very reliably. And clearly not when there are multiple floors above you. So to estimate first the location of the person on such a street map, what we have is, so the streets are represented by a graph. So we have vertices, which are typically the intersections between streets, and edges, which is kind of a city block length street section. And the location is represented by on which edge the person is right now and the distance from the start of that edge. And then if you want to do Bayesian filtering on such a model, then there are typically those two steps, prediction and correction. That is also typical, for example, Kalman filtering or particle filtering step, where in the prediction you predict how the person moves along the edge given the previous position, and also how your uncertainty changes based on that prediction. And then you update the estimate using the most recent GPS reading. What we use for inference is actually a raw black-equalized particle filter. So I'm not going to talk about particle filters, but the idea is you keep track of multiple hypotheses for where the person might be. And initially you might say this is not really necessary for GPS, but I'll show some examples later on where that makes more sense, where each particle contains, in a sense, a Kalman filter. So a Kalman filter is a Gauss, in a sense, represents the position of the person by a Gaussian distribution. So you can imagine you have now a Gaussian distribution on the graph structure. Okay, so it's a 1D Gaussian actually only. And what we sample are things, for example, when the person moves over a vertex, an intersection in the street map, and you want to predict where the person will be, then you don't know yet perfectly well whether the person will go left, right, or straight ahead. So we use a particle representation to sample that. So we guess which way the person will go. And I'll also briefly mention like how we learn those transitions then. Here's just a trivial example. Don't take that too seriously, but you can see the box is the GPS measurements, and the red ones are then the particles or the Kalman filters in a sense. And what is tricky sometimes when you don't get GPS anymore, then those guys of course have no guidance anymore in a sense, right? So, but the nice thing is using this representation where each point is a Gaussian is that if you get GPS back, okay, you can really nicely guide your particles back to those GPS, because what we do is we have a GPS measurement, we have a particle location, and then we compute using A star the shortest path between the particle through the street map to the to the GPS, and then you can just do a 1D Gaussian Kalman filter update. Okay, so if you would only sample the locations, then you actually can't do these things, right? They need to guess the right position when the GPS comes back. Yeah.
So in this example, you're running a forward filter, right?
Yeah, only forward filtering.
But you could have investigated running smoothers, where you basically, once you reacquire the GPS, you infer the most likely.
So we do smoothing when we learn the parameters of the model. I'll get a bit, or we can talk about that. But here we are only interested in online estimation, what's going on. Okay? Yeah, with smoothing you would get better results. So now that, in a sense, we can track the person on the street map, but we also want to, for example, infer the mode of transportation, and we can encode some kind of knowledge we have into the system. So, for example, that depending on which mode of transportation, you also have different velocity distributions. On the car, you can drive much faster than, for example, when you're walking. Okay? Other things, buses are typically constrained to run on bus routes. You can only get on the bus when you are near a bus stop. And you typically can only get on the bus when previously you were in the walking mode, because people don't jump from the car in the bus. Things like that. Okay? Then also we assume, in one instance, that the person has only one car, and this is the only person driving that car. Then what you can do is you can keep track of the car location. So for example, when the person then gets off the car, per particle you estimate where the car was parked, and later on the person can get back onto that car only when it's near the car. Things like that. So we
Very
can
practical usage. Lots of people lose their cars.
see. So, and in a graphical model, dynamic Bayesian network representation, you can just nicely represent all those contexts where here we have the GPS reading. These are random variables that estimate the location here of the person over time, and here we have the mode of transportation. So you add, in a sense, different layers to your representation. Let me give you one example. So here what you'll see is the squares against the GPS reading, then you have these different particles, and now each particle has a different color, and the color indicates the mode of transportation that is associated with that particle at that point in time. Okay? So we sample the mode of transportation. See? So blue means the person is actually waiting here at the bus stop. These little circles, they are probabilistically how we snap the GPS reading to the street map, because GPS is actually in free space. So now the person got on the bus, it's nice green, and in between you see there are always some blue particles popping up, and this is because the bus drives by a bus stop, so the person might actually got off the bus, but we don't know that yet. Okay? Here, I think actually, yeah, the bus moves up here, but the person gets off the bus and now walks. And here you can nicely see these little circles that, in a sense, randomly estimate or guess which street that GPS reading actually belongs to. You can see now that it's actually pretty far off the street map here. But we can easily track that. Okay? So now the idea is we can track a person, we can estimate the mode of transportation, and we can even estimate when and where the person changes the mode of transportation. So now we want to add a layer of complexity in estimating, in a sense, routines of transportation routines, what the person is doing. Okay? And what we mean by transportation routines, I explain by this very beautiful animation. So the idea is a person goes from home to the workplace. Okay, and how does a person go from home to workplace? Well, first walks to the bus stop, then takes the bus and gets off the bus at bus stop B, okay, and then walks to the workplace. Okay, so this is what we mean by transportation routine. So on the high level what we have is goals. We can talk a bit later about goals a bit more, but right now we just have locations where the person spends a significant amount of time. So we don't reason about types of goals. And then trip segments means how you move between goals. Okay? In this case there were three trip segments. First you walk, and then you take the bus, and then you walk again. And we would like to learn those transportation routines just from sequences of GPS traces. So in this dynamic Bayesian network you can nicely model that by adding, in a sense, two new layers, where here we have a section that estimates which trip segment the person is on, and here we estimate what is the current goal of the person. Okay? And we really estimate a full joint posterior over that using this particle filter representation. So how you do this with particle filters is, in that, well, you just add to each particle new portions of the state space, and here actually each particle maintains a full distribution over the goals where the person might go. Okay? And the reasoning, the inference is actually similar to the abstract hidden Markov model introduced by Hang Bui. So now what we want to learn is we want to learn the model, which means there are two parts to that. First of all, we want to learn what are the goals of a person. Okay? For doing that, we actually have a very simple heuristic, and I'll show that on the next slide. And we want to learn also the transition parameters on the street map, which means given that the person has a specific goal, conditioned on that goal and conditioned on the mode of transportation, for every intersection in the street map, we want to know the probability of the person moving straight, left, or right. Okay? So we want to learn transition probabilities on the street map for the intersections. Of course, this is a sparse representation where if you've never seen data anywhere, then you just use a uniform distribution. Okay, with no preference. And the training data is 30 days. Okay, and the key idea behind that is, again, you want to use the data of a person to learn a customized model of this person's transportation routines. Again, the goals is where the user just stays for a certain period of time, and I'll talk about that, how we can improve that actually. And trip segments are places, trip segments contain like how the person is moving, and they start or end typically at bus stops or at parking lots or at these goals. Okay? Let me just give you some example of what we extracted from the data. This is data from Lin. So these circles are the goals that we extracted, okay, and we labeled them, right? So the system didn't come up that this is a grocery store. The black lines indicate the most likely routes the person is taking between those different goals. I'll just show you some other information we can learn from the data. And this is going back to Rick's question about the smoothing. To learn the transition parameters on the map, what we use is we take these 30 days of GPS data and perform forward-backward smoothing, in a sense, right? And then we use EM to learn the transition parameters on the map. And transition parameters means on between the intersections and also between modes of transportation. So we learn where the person typically gets on the bus or off the bus and things like that. Here's something that the model in a sense contains. So what you see here in color are those segments in the map for which the model has a pretty strong prediction of what the person is doing. So if you tell the system now, the dynamic Bayesian network, the goal of the person is this location here, then the system is actually pretty certain about those transitions in the street map, which means the person typically, for example, comes by car from up here, parks the car here at this parking lot that we also learned, and then walks. Blue is walking to the work. Or the person comes more often even from here, parks the car here or there and walks, or takes the bus, gets off the bus stop here, which is near the parking lot, and then walks to work. Okay, so the system, with these transition probabilities in a sense, encodes this information. Then if you now look at the same area in the map, but you say the goal of the person is actually home, then you get, of course, very different transition parameters. And now the system tells you, well, typically the person walks to the bus stop or parking lot or this parking lot, then drives his way to home. This piece is not contained in here because that is actually the location coming from a friend's place. Okay? Now, we can use the DBN actually to on the fly predict where the person is going, or we can estimate that. So what you see here is, in blue are the different goals we learned. The size of each circle indicates the probability that that is the current goal of the person. And the black line, so here down is where the person is, driving the car. The black line is the most likely path the person will take to the most likely goal. Okay? So you see that the person is going up. Didn't start yet, let's see. Yeah. Person is moving up here. And this is the home, so it also has the highest probability. The second highest probability is actually up there in the upper left corner. And now the person decides to actually go left, and then you can see that has this long-term prediction capability that the person is actually going to that location, and the route we can predict pretty well. Okay? We also evaluated how far in the future you can actually predict where the person is going. So in the flat model, what I mean by a flat model is a system that just takes all the GPS traces, doesn't reason about goals, but only for every intersection, in a sense, learns the transition probability for where the person will go. It doesn't reason about goals. And what you get there is that 50% of the time you can predict 5 city blocks into the future. Okay. Now, using the hierarchical model that also reasons about goals, 50% of the time you can actually predict 43 city blocks correctly into the future. So the hierarchical reasoning really gives you also a much better predictive capability. Now, once you have such a system, you might want to detect when the person is doing something new, or when the person is doing something that is not correct according to some notion of correctness, let's say. We can add that by having another layer in our network that's called the behavior mode, and we have 3 different types of behaviors, which is normal, which means you're doing what you've done in the past. Error means the system knows where you are supposed to go, but you're not following the route that you are supposed to follow to that goal. Okay? And unknown just means that the system sees something that it hasn't seen before. Okay. Now we implemented that, or this also, especially Don Patterson did that as part of his thesis. So we took a cell phone. Okay. Then the interface, you can see that our research is not really into user interfaces, but the interface, let's assume every location is represented by a little picture we took of that location. Now imagine you ask the person, where do you want to go? And the person, let's say, clicks on the home location, okay, which is here. Then the dynamic Bayesian network, in a sense, knows that these are the typical ways the person uses from going to work home. Okay. Then we ask, okay, do you want to go by car or by bus? And let's assume the person says, oh, by bus. Then in the dynamic Bayesian network, we, in a sense, we instantiate the trip segments to be the bus trip segment. Okay. This is represented by this being then the real path that is expected. And now let's assume the person gets on the bus. And we reason about those different possibilities, that something new is going on, an error. Right now the bus is actually going up the right route, so there's a very low probability of error or novelty. And it turns out that the person took the wrong bus, which has the same route initially with the correct one, but at some point deviates from the route the bus is supposed to take. And this will happen pretty soon. I think now actually the bus will go left, it's supposed to go straight, and the system now detects that this is actually with very high probability an error, which means that the system says, given that this is your goal, and given that you're supposed to take that bus, you're doing something wrong, something very unexpected in a sense, right? The novelty probability is low because the person actually took that bus in the past pretty frequently, but going to a different goal. Okay, so we can somewhat distinguish between those different errors. And now you can imagine, and this is why the system is called opportunity knocks. So the cell phone now gives a knock-knock sound and says, hey, it looks like you're doing something wrong. And it actually connects to the Metro Seattle-King County transit system and asks for, given that this is where the person is, and the goal asks, in a sense, on the fly, what should be the next bus the person should take, and then guides the person to that. Okay. Again, you can see the user interface is clearly something not you wanna give your grandpa, right? So there's clearly much more work to be done on that level. And the inference is actually here in this system not running on the cell phone, but the cell phone just sends stuff back to the server, and then the server does the inference. But it's perceivable that you can easily do that on a PDA. It's efficient enough, I think. Yeah.
When it experiences and sees an error, what about reasoning about perhaps a change in the goal the user? Like for instance,
good point. We don't do that right now, or we didn't do that there. You could imagine that you have some probability of switching goals, and then in general it gets really complicated. Also, the person might on purpose do something different, right? Something totally new. So how does your system react to that? And then also you would like, for example, to update the model, right? We right now say we get 30 days of data, we learn the model and then apply it. But you want to do a continuous learning. You want to add new goals, you want to remove things and stuff like that. So we haven't really done any of those yet. Good question. Now let me talk a bit about significant places, so which means we don't just want to reason about goals, but we also want to know what these goals are of the person. So, in a sense, we really want to use the information we get from the GPS data to label places such as this is where you live, your home, workplace, or this is a shopping place. Okay, and the model we are using there, I won't go into any details, is instead of dynamic Bayesian networks, we're using conditional random fields. So, rough ideas, it's an undirected graphical models, it's trained discriminatively, it doesn't have these nice predictive capabilities of a dynamic Bayesian networks in a sense, but the representation allows you a huge amount of flexibility in using features to do your inference in a sense, because it doesn't make those independence assumptions that, for example, a dynamic Bayesian network typically makes. Again, I'm not going to go into details, but we can discuss those later on. Just briefly, for inference, we're doing loopy belief propagation because the network has loops, so it's not just a single layer system. And for learning, for those who know, is pseudo likelihood. It's extremely efficient. So we can learn a model based on, let's say, a week of data that takes a minute. Okay. The type of features, the type of information we take into account are things like what is the duration you spend at a certain location, which time of day are you there? So for example, if you're somewhere at midnight and you spend there 12 hours, that's likely to be your home and you're sleeping. Okay. Other evidence we get from MapPoint actually, for example, is there a restaurant nearby? That if there's no restaurant nearby, it's very unlikely that you're dining out. Transition relations, so for example, if the activity 5 seconds before your current activity is driving the bus, then it's much more likely that your current activity is still driving the bus. Okay, things like that. So this is more like temporal constraints. Spatial features, for example, you can drop someone off if you are near a significant place and things like that. Okay, and other constraints, that's actually more technical, interesting work that Lin did, where he uses fast Fourier transforms to efficiently compute aggregations over hidden states. So, for example, you might want to constrain your model to take into account how many homes your system has. So you don't want to come up with a solution that says this person has 10 different homes. Or you don't want to come up with a solution this system has 0 homes, this person. Okay, so we want to bias the model to come up with reasonable numbers of homes, 1 or 2 maybe, and the same for workplaces. The problem is, in order to infer the places from GPS data and to construct your conditional random field for those places, you first need to know where they are, and we don't know them yet, right? So this is part of the inference. So this is called structural uncertainty, and in a sense what we do is we construct the model based on the inference we are performing. Now I'll just give you one example for how that works. So here's a GPS trace over, I think, a week. Okay, you can see some noise over here. So the person moved down here multiple times. On the low level of the conditional random field, we first segment the trace into, I think, 10-meter patches on the street. And for each patch, we estimate the activity of the person using a conditional random field. This is the maximum a posteriori sequence of the person in that data. So red means actually driving the car. Then, for example, this means getting on or off the bus. This is riding the bus. Then those locations here is where the most likely activity is working. Here the most likely activity is sleeping. So that gives you a hint on where the person lives already, right? This is something like visiting. And what we do then, based on that inference, in a sense we take those activities that give us a hint for a significant place. For example, working is an indication for a significant place, whereas driving the bus through a location isn't really a significant thing. So then what we do is we take those instances of significant activities, cluster them spatially, okay, so the near ones we merge, and then we construct an additional layer in our conditional random field to estimate what type of place that is. And the estimation of the type of place is based mostly on the activities you're performing there. So if you're mostly sleeping there, then it's likely that this is where you live. Okay, and if the activity is working, then it's very likely to be your workplace. Okay, so we construct a hierarchical conditional random field that does this kind of reasoning then in a joint model in a sense. And this is a result then that we get. So there are actually, yeah, here's a workplace. Here we have the home of the person, and things like a place a person is visiting. Here's shopping. This is a grocery store we had in the earlier data. So now the key idea, of course, is that in contrast to the DBN work, these conditional random fields are trained on labeled training data. Okay, so what you don't want to have is, you don't want to get data from a person, ask the person, hey, can you label the first week of your data and we'll figure out what's going on in the other 5 weeks. What you want to have is a model that is generic enough that you can apply to the data of the person without ever having seen that person before. Okay, and what we're using there is, this is actually then the conditional random field. What we're using there is something based on relational Markov networks, which is a relational extension of conditional random fields that allows you to nicely construct conditional random fields and do parameter sharing efficiently. And the idea of the approach is we get training data from multiple users. In our case, we actually had 4 users. So we do cross-validation. So you take the data from 3 users. They label their significant places and activities. Then you learn a generic model. In a sense, you learn the parameters for the features that you're using on the data, and then you apply it to a new person. Okay. So one aspect of that is how accurate are we in determining the significant places of a person, in finding, for example, the home, the bus stops, and things like that. Other work, typically, to find significant places, they just use a time threshold. They say, whenever you stop at a location for n minutes, this is then a significant place. Okay. What you see here is a precision recall curve on the leave one out data for different thresholds. So for example, if you say, whenever the person spends 10 minutes at a location, we call it significant, then of course you have a high precision, which means you have not many false positives. But at the same time, your recall is lower because you're missing many places, because you stop just short at a significant location. At the other extreme, if you say any place where the person spends 1 minute, you get a much higher recall because you're missing virtually no locations, but at the same time your precision is pretty low because you call many places significant even though they're not, like a traffic light. Okay, and this is the result we get with our system. So we are better than any of those temporal thresholds you can choose because we extract the significant places based on the activities you perform and not based on the time you spend there. Okay, here's another result. So for example, these are the different types of places. This is again 4 people, and we trained on 3 and tested on the 4th person. This was 2 faculty, 1 student, and 2 students. Okay, the data, and you can see that the workplace is actually never confused with anything else. Home also. There's some confusion with, for example, a friend's location. There were 5 friends' locations in the data. It was 1 week per person. 3 of those were actually detected as friend, but 2 of those were labeled as something else, which is a reasonable confusion, let's say. But you can see that that we get already pretty good results on that.
The other is the ones that hasn't been labeled.
That
Unrecognizable.
That is none of those. That is, for example, we didn't have in that evaluation, we didn't have shopping and things like that, and dining. It's very difficult just based on GPS to distinguish those actually. Okay. I won't go into that, but in a sense, you can then use that system to nicely, in a sense, summarize the data of a person, right? Like driving home, drive from home to parking lot, and then walk to workplace, where the system now not only infers the driving and the walking, but also that you come from home and that you go to a workplace. Okay, which is very different to the DBN we showed. Now, in a sense, if you want to do similar things indoors, where you want to predict, for example, what is an office of a person, and things like that, GPS doesn't really work anymore. So we are using Wi-Fi-based localization. I'll just give you a brief idea of what we're doing there. We developed, this is work done by Julie Lechner, AAAI, and now more recent Brian Ferris did some work that's going to come out at the New Robotics Conference this year. So the representation we're using is, on the one hand side, a graph representation where the edges represent hallways or elevators and staircases, and rooms and open spaces are represented by these little bounding boxes. So we have a mixed hybrid representation that's actually very well suited to represent indoor environments but also outdoor environments. So you can connect that in a sense to a street map if you want. For the sensor model, for the wireless signal strength, we're using Gaussian processes, and the idea is that you walk around with a laptop through the environment, you get the positions labeled, and now you want to learn a model that can predict for any location in the environment what is the signal strength you expect and how certain are you in that signal strength. And Gaussian process is a nice model for doing this regression, which means, in a sense, you're interpolating between your data, and it doesn't only do regression for you, but it also gives you a notion of how certain that prediction is. And you can also, using hyperparameter estimation, nicely learn noise parameters of the signal strength. Okay. Here's one example of how that now works. We're actually working on, this summer we want to get a system that does Wi-Fi localization on the whole UW campus. So what you see here, this is actually part of the Allen Center. Right? Here's the atrium down there. Okay. Here are the different streets, and back there, that's actually a different building. Right? That's Mary Gates Hall. So we want to be able to track a person through all those buildings. Here, I'll just show you some stuff inside the Allen Center. So this representation is actually nicely suited to, I think, represent most of those things that we might be interested in. Okay. So the gold, yellow is the true position, and the blue is the estimated position. And the estimated position right now is just using the most likely particle, so it's really by far not as good as it gets. But you can see now the person gets in the room, and now most of the particles actually hop into that polygonal area, right? And then with a certain probability they can jump back onto the graph. Okay, so they can switch between those different areas. And we're getting on so far pretty benign data, let's say, at least 80% accuracy on which room you are in, right? Of course, sometimes there's some confusion with the neighboring room. It's very tricky to get 100%. Here's now an elevator. You'll see here, the particles are already trying to get up there. Yep, person already waiting. Or the estimator is already waiting there. So again, now over the summer we want to collect more data and really make that work on the whole UW campus. Oh, the yellow was the true position of the person, based on some labeled data, where the person really was at that point in time. And the blue was where our system estimated the person was. So we're using a particle filter here. These little red bars, they represented the estimate of the system, the uncertainty. Okay? But you can see once you can do this tracking in this graph representation, you can do all the learning that we did on GPS. You can do exactly those things now for indoor environments, for example. And Julie Lechner, she was here an intern last year, she's actually working exactly on that right now. Okay? Then now some more recent work we did with a multi-sensor board that was developed again, especially with Gaetano Borriello in collaboration with Intel Research Seattle, and it's a very small system. It's like up here, and you'll see another picture of that soon. It records data such as audio, different light sensors, the brightness, barometric pressure. I'll show you what that might be useful for. Relative humidity, but we figured out that's actually useless, the sensor. Some of those are not that useful. The compass is not working that well yet, so we're trying to improve that. It's also indoors. Compass is not working very well. Most useful is actually an accelerometer that tells you how to distinguish between walking and running. So in a sense, what we want to do is we want to have this little system, a person carrying that around, and then estimate whether the person is walking, running, driving a vehicle, being indoors and outdoors. Okay?
The compass is using magnet, or what do they use the compass?
I think so, but we're not really using it right now. There's some issues with the hardware of the campus still. But you could, and indoors it's not really working that well, but you could imagine that you actually could learn a predictive model for the compass deviation for the different locations in the environment, kind of a Gaussian process for compass deviation. We were going to look into that a bit more. Here's a new system that I'm sure Gaetano will talk about. We just use it. It's pretty cool. So this is the size. It's like really small, right? And it has a sensor board on it. It has an iMode 2, and it has a USB board. So this is all you need if you want to collect data and do some online inference on the data. And with the USB, you can plug in, for example, a camera and store the data then on that device. Okay, and also connect a GPS to it. Here's some of the data stream you see. The most interesting is, for example, here this is barometric pressure, and you can see here where you have the significant changes. This is actually when the person takes the elevator up or down. Okay, so the barometric pressure actually can help you figuring out whether the person goes up and down. But we just did an evaluation, and it's not always as nice as the data you see here. Okay. The activity model, just a high-level idea is, so you estimate the environment, whether the person is indoor, outdoor vehicle. Activities are mostly things like walk, run, standing, going upstairs, downstairs, driving a vehicle, being in an elevator, cover. So this is a DARPA project. I'll give you some more background on that. So it's situation assessment from cover. Not easy to detect, I can tell you. And that is something that's very much based on Tanzim's work, where they also did an activity model, and they used boosted classifiers to learn, in a sense, the features that then you can feed into the system up here as an observation model. Because what we do is, I think we extract like 600 different features from the raw sensor data using different FFT bands and things like that, and then use boosting to learn the classifiers between the different activities here. So this is just from last week, so don't expect any comprehensive results or evaluations yet, but in a sense, this is funded by DARPA, the ASSIST project, and the idea is the following. The soldiers, for example, in Iraq, they go on a mission, reconnaissance mission or whatever you want, and then they come back, and then they have to write an after-action report. So in a sense, they have to somehow summarize what they saw, what was interesting, what happened. And you can imagine if you just write that down, you forget many things. Okay, and even when they take pictures, they might not always, it's not so easy for them to align that with really where that picture was taken. And the other thing is, you want to store that somewhere, and for example, you want to be able a month or 2 months later to say, hey, give me more information about that building. Right? When did people see something about that building? And then, of course, if you just have it written down, then the soldiers will forget a lot of that stuff. And our idea is to use this little sensor board to automatically generate an after-action report or to support the after-action reviewing. Okay? So that's why they're interested in this. They really thoroughly evaluated that. So they came up with this as kind of a course where they want to estimate how accurate we can estimate the state of the soldier, which is walking, running, going upstairs and things like that. So they came up with this parkour so that you have ground truth locations. Here is one of our team, Alvin. This is a soldier, so they both carried the sensor board. The soldier also had a differential GPS, but they figured out that even the differential GPS didn't really work that well, because sometimes there were thick walls between the GPS, so they mostly abandoned that. They had 4 people from NIST observing that, and also a stopwatch and really recording when they reached a different location, and they were pre-recorded. Now you gotta run to that location, then you walk over here and things like that. I can just briefly, hopefully, let's see, here's one to give you an idea. Get that up. Down there, what you see, this piece, that is the Viterbi path of the HMM estimate. Okay, so where red means standing, yellow is walking, running is this bluish thing. The dark gray background means that we think the person is currently in a car. Black means outdoors. Okay. Let's see, so we can, for example, and you can see, let's say, I'll show you a good portion. I would, if you ask me about accuracies right now, we don't have the ground truth from NIST yet. I guess we're around 80%. So you getting 100% something like that is really hard, especially if you apply it to a person for whom you don't have training data. Okay, and in an environment where you haven't trained a lot.
Problem out of the
So what you hear is the audio recorded on the device. Okay, down here this line indicates where we are right now in the timeline, and you can also see here that's the GPS position. Okay.
All the markers out.
You can see they started running, and the system actually nicely inferred the running over here. People cheering. Then they stopped, and red means also that it went into the stop mode, right?
Want to see?
Now they're running back. Now you could say that you could easily infer that just from the GPS, but believe me, the GPS itself is way too noisy to just infer those things. Okay, so we're mostly using actually the accelerometer data for that.
We got the sandbags. We're headed towards D.
Oh, now what they do is actually they drag a sandbag, and because we never ever had any training data for that, the system actually interprets that as standing rather than walking, because the motion they're doing is very different. It's reasonable, and the distinction between standing and walking is actually not so clear always. Yeah? So here's another piece then, if you go, well, I'll show you some more in the next evaluation. So that gives you some idea of how it works. Then the other test they did was this after action reviewing. So they wanted to see how much we can support kind of the soldiers. They actually went on a mission. They came up with a mock-up little village, okay, and 6 soldiers, a little squad. They went through there carrying the sensor board, and afterwards we had to come up with kind of this display you saw on what was going on in that mission. Okay, here's Sergeant Wharton. He was extremely helpful in carrying the sensor system. So this is actually Georgia Tech system. So they had the camera here, there, and this vest here is also from Georgia Tech. They have 6 accelerometers, and our idea is really we want to have a system that the soldiers actually would prefer to carry. So if you listen to the feedback, they don't seem to be really willing to carry that, right? So our system actually is, if you look at it, highly professional. The camera here placed with highly professional duct tape, okay, and up here that's the sensor board. Okay, so in a sense, with the new system that Gaetano built, we can collect all the data I'll show you with these 2 systems. Okay, so here's a webcam that captures an image every second, and the activity model is a bit more complicated, but I don't want to go detailed. Let me see whether that now works. That's a walkie-talkie they really use, so they talk to each other. So this is none of our. No, it's not our system. But let me see. So this is now an after-action review in a sense. of the data. Then, for example, you can walk through that data. Let me show you this. This is the lower resolution, but you can, in a sense, let me play that for a moment.
Gentleman in the plaid shirt on the soccer field.
Here you can see then where they are. On the right, you can see the stream of camera images. In that run, the camera was not placed very well. Down there, you see like a little film strip.
Can we get a video image of that person over?
Roger that.
Then we also actually automatically extract from the data stream. We do boosting, Viola-Jones boosting to extract faces, which gives you quite a bit of false positives, as I guess many of you know who applied that. So in a sense, we manually just go through them and then delete the false positives quickly, but that is pretty fast. So we can then mark those in the timeline down here to indicate to the soldier when we think there's a face that you might want to look at, right? Then we also extract portions. So this is, they really came up with a real mock-up village where there were people playing soccer and they had to talk to the fruit merchants and all these kind of things, right? And there were doctors, and it was pretty substantial, honestly.
A couple guys talking.
And the feedback from the soldiers, at least, is very, very positive. They say the system would help them quite a bit.
Over there with the
Okay. And again, down here you see the inference. So now the system thinks that soon the soldier is actually entering a building, right? This is a light gray area. And the idea is that now, if every soldier carries such a little system, then you can combine the data from multiple. And if you collect data over, let's say, multiple months, then you could extract long-term patterns about what is going on in a certain region. Okay. So now you can see the person actually enters a building, indicated by here this gray. This is now one of the doctors. They're talking to them. So we can discuss that a bit more if you want later on. I think like 8 hours easily. We don't have too much experience with this new system that they just built. So they just came up with that. It came to them 1 week before the evaluation. So over the next months we'll find out more. Just briefly now with RFID tags, for example, now getting back to the more like, for example, elderly people. So these days you can put RFID tags on virtually on many things in the environment, and if a person then is wearing a bracelet, then you can keep track of which objects a person gets really close to and interacts with. And the idea is that based on those sequences of objects you touch, we want to estimate the activities a person is performing. And right now Intel, they have a much nicer bracelet than this, even though some might think this is beautiful. This is also from Don's thesis. So he actually tracked breakfast activities. So he in his house put those little RFID tags over here, right? With his glove, he tracked when he was interacting with those objects. And we get actually pretty good results. So here's the ground truth. So the person was first making espresso, then make oatmeal, then having breakfast, guess making more oatmeal, I don't know, breakfast, and then clearing the table. There are some interesting aspects. So for example, on the one hand side, you don't want to distinguish between which specific fork you're touching, right? Because the next morning you're certainly going to use a different fork for your breakfast, right? So you want to, in a sense, abstract away some information, and this is what they call this relational smoothing or hierarchical smoothing. But on the other hand, to distinguish, for example, between having breakfast and setting the table for your family, the best way to distinguish that, because the type of objects you're touching is very similar, right? It's a fork, knife, and things like that. But when you are having breakfast, you much more touch only one fork and one knife, right? The one you're using. But when you're setting the table, you're touching many different forks and knives. So this actually is something where it helps you to distinguish between different activities, okay? And we have a technique that actually can take this into account, and can also take into account that even in your training data, if you only use a coffee mug to drink your coffee, but then later on you have data where the person is using, what else do we have? Coffee mug and a cup, a little coffee cup, thanks. Then you want to transfer that information, right? And not just see like, oh, I've never seen that in the training data. So we do these kind of things. So with that, I'm right on time. Conclusion. So first of all, the location of a person really provides a lot of context of what the person is doing. And for doing this spatial reasoning, I think this graph-based representation, especially the hybrid representation, is extremely powerful, because it gives you, in a sense, already a partial discretization of the space, because you have these discrete transitions on the graph, right? Which, if you just have a free space representation, is not so easy to find anymore. So it's very nice to learn things about from data on these graphs. Shouldn't be new, but these hierarchical representations like dynamic Bayesian networks, conditional random fields are extremely powerful to really give you these higher level notions from the raw sensor data. And yeah, I think this is just a totally exciting area, and there's a lot of stuff that is still to be done in order to make it really work. Ongoing project is, again, this assist I just talked to you with the soldiers. So we hope that there's going to be a 1-year extension on that. Where we then want to look at multiple soldier data and combine that and figure out when they're searching a building together and things like that. So in a sense, getting more to the higher level activities. KLO is also a DARPA project that they give quite a bit of money to SRI every year, and SRI subcontracts, and it's mostly related to machine learning. It's a cognitive assistant that learns and observes, so it's kind of something sitting on your desktop, but you could imagine that something like that is also on your laptop, so your laptop knows where it is and things like that, and learns those things based on calendar information, for example. Then the social network study, where I'm also focusing on right now, is how people use buildings, so predicting where a person is going and things like that, using more relational model. Elder care, of course, long-term observation of activities, and with Microsoft looking also at maybe some smart navigation systems, so it's very much connected to the GPS data. I think some of the key problems is really learning models that you can transfer between different people, between different environments. For example, with a sensor board, you don't want to overfit your data in a sense, right? And these relational techniques also are very well suited to represent more abstract notion of a model. Model adaptation, so in a sense, with the GPS data, you want to add points to your data, you want to revise your model, but also you want to maybe adapt your reasoning to the specific person that is wearing it with the sensor board. Sparse training data, sparse annotation. We just did some recent work using virtual evidence so that you can just annotate little pieces of your data, and then the system uses that to train the whole model based on it, in a sense, and that works actually pretty well. More context information, so I think we're just at the beginning right now, and the more you can put in your dynamic Bayesian network, the more, of course, you can also infer and learn about a person. Structural uncertainty, which is very interesting. This thing is like, if you want to reason about the significant locations of a person, initially you don't know what these locations are, so you have this uncertainty about how many objects are there, how many places are there, and this comes up over and over again. And doing a nice solution to that is actually very interesting. It's also a key vision problem, right? Like how many objects are in a picture and things like that. And of course, on the long run, unsupervised learning. And I think that's it. Thanks a lot.
Thank you. So I'm going to jump in and ask you a question.
Oh.
A lot of the stuff you're talking about, I was thinking about things like overlaying it with civil engineering and design. Where should certain things be for communities? And I was also, when you got into the interior spaces, it was very much, when you were talking about the kitchen stuff, I was thinking, wow, you could figure out how to design a kitchen around an individual cook. Mm-hmm. You could design how to build a room around a particular set of activities.
Yeah. Yeah.
Have you thought about that step in the past?
So this is very much where we want to go now.
Right.
So for example, with this data that we get from all the students, we really want to learn generic models of how people use a building.
Right.
Right. Like where do they meet? Which places do they prefer? And also just things like that seem so obvious. When do people take an elevator versus the stairs, right? What does it depend on, all those kind of things? So I think this is more like the basics we did, and now we can start doing more the cool high-level stuff.
So the thing I'm really interested in is finding out when you add in to some of the network stuff you're doing, the traffic implications. For example, if I'm in a motor vehicle and I'm taking what you think is a wrong route, if you happen to know the traffic is really bad in a particular place, maybe that's the right route. Mm-hmm. So I'm really interested when you take that next step, integrating some of that kind of data.
Yeah. Yeah, so there the idea is also, if you have this system that knows where you're going, or that is pretty sure about where you're going, then, and it knows which route you typically take, then that system can actually scan for the traffic information that's related only to that route versus telling you about all the different traffic jams you might have. And then it might actually tell you, hey, there's an accident on your route, so maybe you want to go that way. Things like that, yeah. And we're also starting to work, there's a group working in urban sim, so they are predicting more large-scale spatial context, like where do people move and what will be the impact if we add a light rail or if we remove the viaduct, okay? And I just talked to them, and there we also want to get more data, large-scale studies, and then we'll see what we can get from that.
So you thought also about segmentation, classification, profiling, trying to figure out what classes of people there are?
We thought about it, but we haven't done anything. So that's another layer in the model, in a sense, right, where you distinguish between different types of people, in a sense, yes.
So you could predict, wow, this person is most likely a school-aged child, this person is most likely a student, this person is most likely...
The only real caveat is that you need much more training data if you want to do those things. Right, so we need data. John.
Have you thought at all about the long-term temporal relationships between activities? For instance, if you eat, you're not going to eat for
Oh, yes.
a while, or if you run for a long time, you're not going to want to run for a while.
We thought about it, but it's not part of the model. So one thing, so the obvious thing is, yes, that in a sense you want to constrain the inference so that it's more likely that a person has one lunch a day. Right? Some people might have 0, but because sometimes it's really tricky to extract that from the raw sensor data, right? But if you have a model that says, hey, you only have 1, then you could take that into account. It's just, it's pretty tricky actually to take that into account in a model that is also efficient. Some of Lynn's work where, in a sense, what you can do is you can count the number of instances of a certain thing and take that count into account when you do the reasoning using this fast Fourier transform aggregations. But it's tricky if you want to do that on counting number of segments and things like that, because you're counting hidden state, and that is something that is not so easy to do. And that again gets into the structural uncertainty, if you want so. Like how many lunches do you have? But yeah, that's a good point, and we're looking into that more and more. Yeah?
I was just wondering if you could estimate the walking and running speed from the accelerometer.
Pardon? So how do we...
From the accelerometer data,
estimate the speed. So we estimate, so what we do in this system actually, we take into account the accelerometer data, but there we only distinguish between the discrete states, in a sense, walking, running, and standing. But we also we also take the GPS velocity estimates and feed those also into the model. So those you could then, in a sense, it's mostly GPS that we would use for that. We're not doing any velocity estimation based on the acceleration.
So is data good enough for that? Is data good enough for that?
You think whether it would be feasible to estimate the velocity?
What your detectives doing? I mean, with multiple accelerometers, they can look at these things.
Yeah.
I think if the
But it-
might be very noisy.
So I don't know.
Yeah.
Question.
What you can do is, in a sense, you can have a model that counts steps. But then, estimating the size of steps and things like that, maybe then if you add gyros and accelerometers, you could certainly do these things. But the question is whether you really want to go there to require a person to wear all these sensors. I think a step counter might be reasonable, but it's not so easy actually.
Yeah, because it would be useful. You can say what you estimate the distance, right? It can be useful when you know how much they walk, how much they run.
You tell
But-
this thing, right?
Pardon?
Wear a little 2D accelerometer on your shoe, right? Gives you the mileage and
Yeah, those pedometers in a sense, yeah.
and
Yeah.
it's essentially doing a combination of velocity and integrating the accelerometer plus step count.
Yep.
But I thought they only calculated how many steps you
No.
do. They calculate distance?
And
Oh, they calculate the steps and then have an average step size.
Oh, okay, that's what they do.
but they do
I think
adjust
so.
the step size based on the accelerometer itself.
Yeah, okay.
I use
This-
these things, and I have friends who use them. We're very different sizes and very different runners, and they're pretty accurate.
Oh, okay. I know of one system, I think Honeywell is building that, it's a DRM dead reckoning module, and they actually, when you're outside, I think that's at least what they say on the website, they use the GPS kind of as a ground truth estimate for how far you move, and use that to adapt your specific motion model, so that they estimate how big is your step size. based on the GPS, and then you can use it when you're indoors. Right now, we would get the distance you're walking mostly from GPS or Wi-Fi.
So a couple of comments. One is that I thought that you could also explore certain structural constraints between activities to help you to the learning, such as if actually someone is doing eating something, then the probability of running or some other activity will be extremely low. So these are sort of mutually exclusive constraints. I don't know if you already have a...
We do have some of those constraints in this model, right? So, for example, if you know that if the person is outdoors in the environment, the person is not going to use an elevator, right? So constraints like that you can actually. Right? So we're using Jeff Bilms. He has his graphical models toolkit, GMTK, and once you know how to use it, it's actually very, very cool for doing these things. And you can automate parameter learning, smoothing, Viterbi, whatever you want. It's extremely good. That's what we are using here mostly. And also the undergrad is actually implementing a raw Black-Rice particle filter for doing this kind of reasoning.
Another comment is that your learning of activity is actually based on the data and the frequency of the data. I don't know in the applications here that arise, but for some of these response activities, they're actually interested in learning abnormal behavior.
Mm-hmm.
The behaviors that's very infrequent, but something that they want to spot right away. So I wonder, what you might actually take where the data is very small.
Yeah.
I said it's very small. It's very infrequent. It's not just an anomaly. You want to recognize.
Yeah. So my feeling is, to do this, the more you know about the normal behavior, the more capable you will be in detecting abnormal behavior. So maybe standard techniques, what we do here to detect when the person takes a wrong bus and things like that, right? That might be an instance maybe is you just look at the likelihood of your data, right? And if it really goes down, then that tells you that's something your model really hasn't seen before. But it's, of course, if you really want to, in a more complex scenario, it's certainly not that simple anymore. And we're just starting to get there, but that is also a long-term goal. Learning patterns and then learning deviations from that. It's also for these elder care long-term health monitoring, right? If you learn what the typical patterns in performing activities of daily living is, then the tricky piece is it's not so hard to detect when they do something really wrong, right? But if you have these slow changes over let's say weeks of periods of time when they get less and less active, then it's actually very tricky to detect those. And we haven't solved that at all yet.
The third comment is that most of sensors talk about our wearable sensors. I assume that the same would apply to instrumental sensors. In fact, you could actually use the environmental sensors together with wearable sensors.
Sure.
There's some interesting privacy issues. You've probably heard about Cricket Project where they have this. Basically, it's actually the device that people wear or people carry actually initiate the distance estimation, so that location information is actually owned by the person.
Yes.
The person can decide what to share or not. And so I wonder if you ever thought about those issues, the trade-off between the infrastructure sensing, the wearable sensing, and the combination of those.
I think that's actually a key advantage of those techniques, as you said. So, even with the Wi-Fi localization, right? I think if it's my PDA that knows where I am, people are much more likely to accept that versus if the environment is tracking you, right? But for cameras is a very tricky issue, right? So that's why we're also not using cameras at all, because I don't think we could even run many experiments in the building because people just wouldn't want to have the cameras there. Of course, there's always this trade-off between how much it helps you, right? So, for example, we might not be willing to accept anything that is really observing us in this building, but an elderly person at home, when the alternative is this technology allows you to stay at home for another half year versus going to a nursing home right away, they might be happy to just do it, right? Because they might also feel safer.
Right. Or you can actually define the sharing group such that only the relatives or people who care about the elderly can actually have access to the doctors.
So Intel did, of course, some research, also some great stuff into that area where they just see how willing are people to share even their location, right? So do you want your boss always to know where you are, or do you want your spouse to know where you are? Maybe not always, right? Or even your friends, right? You might. There's this typical standard example is like you have a dinner invitation, right? And if the host knows your location, then you can't just come up with this nice lie anymore. Or there was an accident, or there was a traffic jam, right? When the host exactly knows, no, you're still at home, right? So these kind of things come up then. And
you want to actually talk to a few legal scholars at Berkeley, Pam Samuelson
okay.
and Deidre, I forgot her last name. They've been working with the Berkeley Trust Center, which actually does a lot of interesting security research for the ubiquitous computing environment. And they've been actually thinking about very interesting policy issues that relate to privacy. I just was there about a few weeks back, and there's some really interesting thoughts. So
that might make sense. Yes, that would be great, because it's a very tricky issue with privacy. Yes. What?
Another thing is actually you have the Wi-Fi and GPS, some of the indoor sensors that can. Do you have some of the work to integrate with the white cane or for some of the visually impaired people to do the indoor navigation system? Or? Because to me, you have the Wi-Fi already, you can locate some location, and once you have to integrate with some white cane or stuff to be deployed to blind people or anything to be.
Yes.
And if you have a underlying the layout of the building to be at the back end.
Yes.
Basically matching with the building layout, you learn the significant point. For example, like the drinking fountain at restroom or anything, and you can share it with your other peers.
Yeah. So I just saw some really nice work. Stergis Romeliotis is working on that, where they actually put gyros and different sensors on a white cane to estimate the location of a blind person. So with Wi-Fi, I wouldn't really want to go there, but there's some work going on right now. Henry Gaetano, they're working with the rehab department of rehabilitation medicine on, for example, cognitively impaired people. They have to go, even if they live, let's say, in a nursing home, they have to go to physical therapy. So you don't want them to get lost there. So they're looking into a device that can guide those people through the building. But they are right now doing some Wizard of Oz studies where you assume that the system knows the location accurately. So I'm now also getting more involved in that, in combining exactly those systems to that. And then the question is how accurate does it have to be for this?
Thanks.
Thank you very much.